Hello, and thank you for joining us for part 2 of our GC column series, Method Development. Our presentation will begin with Amy Nutter, VOC Applications Chemist for Teledyne Tekmar. Then Amy will introduce Chris English from ResTech Corporation. We will be taking questions, so please feel free to submit the questions throughout the presentation, and our presenters will follow up with you after the webinar. This webinar is being recorded and will be available within a few days. Now I'm going to turn it over to our first presenter, Amy Nutter.
Thank you for the introduction. I'm Amy Nutter, Applications Chemist at Teledyne Tekmar, and today we have Chris English, Laboratory Manager at ResTech Corporation, to give us an overview of part 1 of our series, which was all about chromatographic separation and how to choose the correct column for your purge and trap volatiles analysis. And he will also walk us through ResTech's Pro Easy GC tool for method development. So I will cover a quick overview of the purge and trap technique and our products. Chris will give an overview of that chromatographic separation, typical column phases, GC configurations, and film thickness, which was all part 1 of our series. So if you missed that, go ahead and go on back to part 1 to rewatch that. And then he will get into method development using Pro Easy GC, and then he'll tie everything all together at the end. And so be sure to submit any questions you have, and we will be able to answer those by email. So now let's get into how purge and trap works. The theory of purging and sweeping the sample with an inert gas, called dynamic headspace theory, sounds simple, but it is a very complex process. Purging a sample to extract analytes is a gas extraction. In purging a sample, the system is no longer at equilibrium. This is because the VOCs that move into the gaseous phase are constantly being removed by the purge gas. Continuously replacing that headspace causes a disequilibrium, in that there is always a higher concentration of VOCs in the liquid phase than in the gaseous phase, creating a net movement of VOCs from liquid to gas, extracting the VOCs from the sample more efficiently and improving sensitivity. Then the gas is swept away onto the trap, where it is concentrated and released to the GC. A basic purge and trap consists of 5 main parts: sparger, flow control, 6-port valve, analytical trap, and the heated transfer line. The sparger is the glassware right there on the front of the instrument that receives the liquid sample to be purged. In purging, the sample extracts the VOCs by dispersing that inert gas through the sample matrix for a preset time and flow. This flow is controlled by a mass flow controller or a pressure regulator that monitors and precisely controls the gas flow rates throughout the entire purge and trap process. From there, the 6-port valve directs the gas containing the analytes to the analytical trap for concentration. By backflushing carrier gas through the analytical trap, the 6-port valve directs the VOCs to the GC for separation and detection. The analytical trap is used to capture and release VOCs swept out of the sample by the purge gas. Trapping the VOCs helps create a smaller band of analytes traveling to the GC column, producing greater signal-to-noise ratios and lower area-to-height ratios, generating sharper peaks and better sensitivity and resolution. Once the VOCs are captured, the trap is heated, causing the VOCs to desorb, and carrier gas is used to desorb VOCs off the analytical trap and carry them through the heated transfer line to the GC. Teledyne Tekmar is the market leader for purge and traps in the U.S., and we offer several different options. The Lumen Purge and Trap Concentrator, shown on the right, is our standalone waters-only concentrator that can be paired with the Aquatech LVA autosampler. We also have the combined autosampler and purge and trap concentrator, the Atomics XYZ, which is shown on the left, which is capable of analyzing soils, solids, and water samples. So now that we've covered what happens to the sample before it gets to the GC, let's get that overview of part 1 of our series, how to choose the correct column for your volatiles analysis, And then we will learn a little bit more about how Pro-EZ-GC can help with method development. Our guest speaker is Chris English, who is the laboratory manager at ResTech Corporation. He has managed a team of chemists in ResTech's Innovations Laboratory since 2004, and before taking the reins of the laboratory, he spent 7 years as an environmental chemist and was critical to the development of ResTech's current line of volatile GC columns. It is a pleasure to have you for this series, so go ahead and take it away.
All right, thanks, Amy. I appreciate the introduction. Just to go over what we've talked about in our previous webinar is finding the right phase. Many times we can go on the internet and go out there and find something that fits for what we're doing. For instance, if we're looking for 8260, we might run into Amy's application that she's done on there, which has been completely optimized not only for the GC conditions, but also for the perch and trap conditions. And that would be completely appropriate. If we have a smaller list, however, we might want to go in and use a different tool or something else in order to get that separation. So that might require an understanding of different stationary phases. And many of these stationary phases were tuned specific to compound lists. So if we have something that's got phenyl in it, that's appropriate for aromatic type compounds. Whereas if we have something like an RTX 200, which is a trifluoropropyl polysiloxane stationary phase, that works well with freons and halogenated compounds. Then going into column length and configurations, from part one, we looked at a whole variety of different configurations, but we can boil that down. If we're using a mass spectrometer, we're going to be using a 0.25 millimeter ID column or a 0.18 millimeter ID column, depending upon how sensitive our mass spectrometer is. The newer mass specs are far more sensitive and will allow us to use lower flows, like a 0.18 millimeter ID, and a higher split ratio, which will actually give us better signal to noise ratios and sharper chromatography. So those would be the columns that we would recommend, or a 0.25 for an older mass spec, like a 5970, 71, or 73 type column. With film and with the internal diameter, we're looking at a ratio for the film thickness, and that is we want a thick film column. And if we're looking at something for an FID type detector, that's going to be a larger bore column. And the idea behind that is certainly it can handle the higher flows, but the more flow we put to that detector, the better our sensitivity, whereas it's just the inverse with a mass spec. And then we also talked about translating methods. And when we're translating methods, we're keeping the same elution temperature. That is, the analyte comes out at the same temperature on the two different platforms that we're looking at. So whether that's we changed carrier gas or we changed the configurations of our columns, the method translator gives us that same conditions, and that therefore we have the same elution order. And that's really key because it's going to make our resolutions very similar and our elution order the same. So if we go back from part one and take just a quick peek at some of these different stationary phases, the most common and low bleed phase is the PDMS, and that's a polydimethyl siloxane phase. It's certainly the easiest one for chromatography companies to make. And then when we talk about any other phase, they're all PDMS based. That is, if I say it's a 35% diphenyl column, that means the remainder is PDMS. So if we're looking at something like a 502 VOC or Bocol, those are all phenyl-containing phases. They do really well with aromatics, such as gasoline and fuels and things like that. However, they don't do as well with halogenated compounds. And that's where the cyano phases came in, with cyano and phenyl added. And those are the 624. Then we had the VRX type phase where we could add just a little bit of fluorine to it and fine tune it to get specific separations. But really the elution order was very similar to a PDMS or a 1 because the substitution was only a couple percent. Taking all of that information and pulling it together and then fine tuning a column, we came up with a volatile mass spec column, and that's called the VMS. And so that was built specifically taking all of these building blocks and coming up with something that was fine-tuned. And really the goal there was to get the trihalomethane's baseline resolved, since that accounts for probably 50% of an analyst's hits in drinking water, and then the TCE and PCE baseline resolution. We can baseline resolve those compounds and then also have good resolution for everything else. We've got a column that's going to work out. So here's our don't reinvent the wheel. This was Amy's work that she did on the VMS with a 20 meter, 0.18 millimeter, and 1.0 diameter film thickness. And again, this matches the cycle time of the perch and trap concentrator. So your perch and trap concentrator is not going to be waiting, or the GC is not going to be waiting. Those two are going to be matched perfectly. So that works out really well. So the one thing we do want to introduce going forward is the ProEasyGC chromatogram modeler. And this is those cases where I'm not running a classical 8260. I might be running a different list, or I have added compounds, or I have specific resolutions, or I want to use a different carrier gas or different column dimensions. So any one of those would account for us going into ProEasyGC. And if we can see in the drop-down menu under chromatograms where it says ProEasyGC chromatogram modeler, we can click on that, and then these are the kind of functionalities that we just talked about, but it's that idea of we can look at any stationary phase that has those compounds loaded in it. And then again, we can look at different carrier gases, we can look at flows, temperatures, time, length, ID, film thickness, and whether it's an atmospheric detector or a vacuum detector, that is mass spec, FID, those kind of things. So in order to get started, we need to log in. So that's your name, your email address, and I think it's only like 4 or 5 different things that you have to fill in there. It's not very difficult. And from there, you can either go in and you can do additional webinars, but what I'm going to tell you today is going to get you started. So you'll be able to go in and do your own modeling and everything just from this webinar. You won't have to go through all of these different things. But if you want more information, down at the bottom here, we have more webinars on that topic. So the first option is going to be the simplest. And this was really in 2012, we came out with the original online ProEasyGC, which we just called the EasyGC chromatogram modeler. And that was, all you do is enter in your compounds into a box, and it gives you one recommendation. And if you didn't like that recommendation, there's not much you could do other than contact our tech service, and we could model it for you. But that was the earliest one. And now this is more advanced in that you're going to enter your compounds into the box, and it will give you a whole variety of different columns that are appropriate for that separation and the conditions that go with that. But just one of the take homes here is that there are 2 ways that you can use this program. We can search by just entering the compounds in here, or we can do option 2, and that is we can pull from a list of compounds. If we know we're running 8270 semi-volatiles, we could pick from there. If we know we're running volatiles 8260, we could pick a volatiles list on a volatiles column, and they would all be in one list. So that's kind of the difference between the 2. The nice part is on your left-hand side, you can cut and paste, and on the right-hand side, you could select all if you wanted. And then that would just be one click away from your modeling. So many customers will go in and they select all for their 8260 compounds, and then they just remove a couple here and there, and they're ready to go. So 2 different ways to do it. So if we go right now by searching in the box, we just entered in our xylene, toluene, benzene, and O-xylene. And what you'll see down here is it will immediately tell you how many columns we have and what the resolution is. So 4 out of 4 resolved. We made this one easy, right? Make it look good. So all of the columns look like they're going to resolve it. And so we can pick any one of these. And if we click on any one of these, it will give us a solution on the right-hand side. In this case, we clicked on the VMS. You have a 30 meter, 0.25 millimeter ID, and 1.4 diameter film thickness. Now, getting ahead of myself, you can click on conditions and change whatever you want specific to that column, or you could click another column and click on conditions and make minor adjustments or major adjustments, whichever you like. So on here, we've entered in this large list. In this case, it's 74 compounds, and we hit solve. And once we hit solve, it basically says that 48 of these 74 compounds have been resolved. And this is the result that it gives us. One thing to keep in mind is EasyGC does not know if you're running matrix. It doesn't know if you have, contaminated samples or you have carryover. And so the conditions that this is giving you is going up to 185 degrees. Like Amy ran in her application, she did a program that looks like this, but then it has a rapid ramp at the end to bake it off. And that's what I'd recommend, is adding one more ramp, which would require you to hit custom if you wanted to add that in here. Or you could just add it when you get to your GC. So this is the actual prediction that you get, and we'll show comparisons of how these predictions, how close these predictions are to actual runs. So here we have, again, these are our 74 compounds. Sometimes what you'll see is you'll see 73 versus 74. That means that one of these libraries did not have all of the compounds that we requested. So there was one compound missing, or in the case of the VRX, there were many compounds that were missing. But it's still giving us that result. Sometimes if too many compounds are missing, it won't even display that column. And we have that with a few compounds, or I'm sorry, with a few columns. And those are areas where we have to add compounds to that because customers are requesting those changes. So now let's go over to option 2. Now we're going to get to search by stationary phase. So we can pick a stationary phase that we already have in-house, and then we can pick a list of compounds that we have, select our list of libraries. And here's the interesting addition to this option 2. We can click whether we want it targeted to be resolved or just selected. So we can select our list, and we don't necessarily need those to be resolved because it's on a mass spectrometer, but then we can click them again, and they're now targeted to resolve. So if you click it twice, it targets to resolve. You click it one, you selected it. And again, what I do is I click them all and then I unselect them, and remove them from my library, because it's easier to add everything, add all 200 and then remove 30 compounds than it is to add, over 100 compounds. So this is what it looks like. This dark blue are the ones that are targeted to be resolved, and then the light blue are just added to our chromatogram. And this is what the chromatography looks like, or the modeled chromatogram. And these are the ones that are not targeted to be resolved, but are added to the chromatogram, and those are the ones that are targeted to be resolved. So we need to find a solution that provides the overall best solution. One thing to remember with EasyGC is we do increments. So we set what the ramp searches look like, and in that case we don't search by 1 degree a minute, 2 degree a minute, 3 degree a minute, 4 degree a minute for multiple ramps, because that would get into 100 million different iterations. So we do have it bracketed, but it's going to give you the overall best solution. But in saying that, you can go in and click on the custom and find a slightly better solution than what we gave you. You might be able to fine tune it. I gave a class over at Penn State University, and the quiz at the end was the students had to find a better solution than what EasyGC gave them for their compounds. So it was kind of interesting to see how creative they were, especially when they were thinking of like Van Deemter curves and they were using a more efficient carrier gases to get to that point, like nitrogen or something. So it was very interesting. But so that is one thing. This gives you the best overall solution, but it doesn't mean that it's that there aren't better ways to fine tune it to get a solution. So in different concentrations, when we first put this out, we had all of the peaks were at the same height. and customers were completely turned off by that. So what we ended up doing was we adjust the height, the peak heights, to make it look more real. That has some customers, thinking that it's real sometimes, but it also it makes it look much more natural. If they're all at the same peak height, it just doesn't look. It looks like a terrible chromatogram, honestly. But if we have if we have a high concentration analyte, it might not be resolved from a low concentration analyte that comes out right next to it. And of course, we talk about the sample matrix. It's not only sample matrix, and we'll show this in another slide too, but it's solvent effects. So things that happen in the inlet at the front end of your chromatogram can affect the retention times of analytes and the peak shape and resolution. And so those are things that are not predicted by EZGC, and matrix effects. So things that interfere with your compound or distort the peak shape EZGC is not going to be able to predict that. So here's the custom conditions that we can click on, and that's the next tab over. So we got our solution, and our solution is displayed on the right-hand side. And now we can click down on the custom button down at the very bottom right-hand corner down there. That allows you to change whatever you want, basically. You can change your oven program. If your oven program is unrealistic, it will highlight it in red. If you have chosen a column that the mass spec is going to pull a vacuum on because it's too short, like if it's a 30-meter 5-3 column, the mass spec's it's going to pull a vacuum right through. So you'll have a negative value. It'll also give you a red value. So anytime you see a red value on the screen, it means you're doing something that's not going to work. So, because we'll have customers call in and say, I don't understand why I can't put a 30-meter 5-3 in my mass spec because I'm trying to model it here. And again, it's going to be pulling vacuum on it. You won't get, your chromatography is going to look terrible. And the same thing, if you put 120 degree a minute ramp rate, it's going to highlight it in red. It will still give you the result though, because there are, like Hyperchrome has an instrument that can do 120 degrees a minute. So it is possible, but we do want to let you know that most conventional instruments cannot do that ramp rate. And then you can look at constant flow, constant linear velocity, whatever you would like down at the bottom as far as flow considerations go. So here's our predicted versus our actual. And the hardest part for us is predicting peak widths specific to compounds that come out very closely. And so this is a classical, if we look at peaks 33 and 34, this is like classical chromatography, what it would look like under a perfect set of conditions. And then if we look at actual, we'll see that those two compounds are not resolved, 33 and 34. So some of our results show things as slightly better. And we're trying to make adjustments to that without compromising the other predictions. And that's going to be another iteration of EZGC because we're continually updating EZGC. But this is as it stands. Now, if we take a look at the front end chromatography, again, we can have solvent effects at the front. And if we're thinking about something like purge and trap, if there's a lot of water that's at the front end, then that can affect the chromatography as well. So these are the constraints that we were talking about. If it's not in our modeling, if we haven't added it to the EZGC, it doesn't exist. So there are about 8,000 compounds in there on about 24 different stationary phases. And again, we can have solvent analyte focusing. When we were developing EZGC, we ended up running into the solvent analyte focusing issues. And so there's an article on LCGC that you can look up. And if you just type in analyte focusing LCGC, it'll come right up. But it discusses this in detail and the things that we found on that. So this does assume that it's an ideal injection. So a headspace with a high temperature headspace work where you're going to have a lot of DMSO can actually affect the chromatography as well. And we're assuming that it's 100% Gaussian. But the differences, of course, are not that great from what we show. But if it may be the difference between getting a partial resolution and no resolution at all. So, and then of course, concentration of compounds. If we're looking at one hexene purity of one hexene, the analytes on either side of that may not be well resolved because we've got a peak width that's, a minute wide because we're looking at purity things. So that's another thing to take a look at. Here's just an example for an EZGC chromatogram. The actual retention times are different, but the actual resolution looks pretty good if we look at this. And then of course we'll see down at the front end doesn't look anything like the modeled chromatogram. So that's gonna show that things look really good. And part of that is the starting temperature. If we have a low starting temperature, we can get better focusing than if we had a higher starting temperature. And we can show that in this slide here. So we have a 60-degree starting temperature versus 70-degree starting temperature. And even that makes a difference. So now if we want to go ahead and save our work, we can go into the My EZGC, and I have like literally hundreds of things in there saved. If you've called me and asked me to help you with modeling, I have it here. So if you want to add a compound, you can give me a call and I'll add it in. But we click on My EZGC, and the first part is to name it. And then once you've named it, you can click on the pen there to name it, to activate this box. But then you want to click on OK. If you don't click on OK, it doesn't save it. And it'll just save it as method 1, and then it'll just keep overwriting your previous method 1. And then once you've clicked OK, then you can hit the save button. And then it'll add it here. And it's, from what I can tell, it's an unlimited number of things that you can save in there so far anyway. I haven't reached the end yet. So if we're tying all this together, we can optimize chromatograms on many different stationary phases. For volatiles, we have close to a dozen different stationary phases in here that you could model from. So, and that includes the 624, the 624 SIL, the 502.2 column, the 20 column, and then the VMS column as well. So there's a whole variety of different stationary phases in there. Even the RTX 200 phase, we have volatiles on. So there's a whole bunch of different phases. Some of those, they may be listed as solvents as opposed to volatiles. That's the only thing. If you're looking at it under option 2, you might look under solvents and you'll find it. And if not, you can just paste it into the box for your option 1, and it will pick all of those different phases you can look at. And that's not even to mention the RTX1, which has a whole variety of different volatiles on it as well. So different column dimensions. It's going to give you a column dimension, but if that's not the column dimension you want, you can click on the conditions tab, and then from that drop down, pick a commercially available column dimension. And of course, if there is a very specific separation that you need to do, you can click custom and come up with a custom column. We had some people that were doing Freon and Freon breakdown research. So it was how Freons react under UV light atmospheric conditions. And they had modeled 120 meter RTX 200 by 0.25 millimeter ID by 1.0 film thickness. And they were modeling that. They ended up buying two 60 meter 2.5 columns and then connecting them together to get what they were looking for doing their Freon research. So it's kind of interesting. So there are those occasions where you might want to come up with something. But generally for the volatile work and for what we have, you'll be able to just pick one of the existing column dimensions and use that. So you can make your own selected oven conditions. And again, you want to take that into consideration with your starting temperature. You don't want to start with too high of an oven temperature. You're going to compromise the volatile resolution at the front end of your chromatogram. Again, you can switch carrier gases if you're looking for nitrogen or hydrogen. You can look at those two as options. So depending upon what you're doing. And then between whether you're doing an FID, which is pressurized FID, PID, any of those types of detectors versus a mass spectrometer. So nice part is, you know, you can go in and take a look at it. There's really no risk, and you can save that. And if you have any questions on it, you can simply hit the help button and it will send your list to tech service, and tech service will be able to pull up exactly what you're looking at and be able to help you with it. We have many people that it's kind of the too good to be true situation where they enter in a series of compounds. They say, do you really think this is going to work? So they send it to tech service to say, I mean, if this really works, I'll buy the column. And the answer is yes. Like, you can certainly, this is basically your guarantee that if you get that and it doesn't work, we will return your money to you. So that's the other thing is we get a lot of those where people just send us their conditions and say, you know, do you really think this is going to work? Because it looks too good to be true. And then the other thing is we definitely have it in, you know, we have it translated for different languages as well. So.
All right, thank you so much for joining us today, and I want to give a big thank you to Chris for joining us, and thank you for your time today. Please check out our website. Yeah, please check out our website for all of our latest application notes, including US EPA methods using ResTech VMS columns. You can view past webinars like part 1 of our series, or you can listen to our podcast too. And please be sure to visit our online store, and you can follow us on social media too. Thank you so much.
All right, thanks.